All right, we're going to go ahead and get started. Hello, everyone, and welcome. Thank you for choosing to spend your valuable time with us. Today's webinar will cover the basics of wolfBoot and all the advanced things we have been adding in the last year. Presented by engineer Daniela. My name is Emma, and I will be moderating the webinar. All attendees will be in listen-only mode. If you have any questions, please use the Q&A box. After the presentation, Daniela will answer your questions, and as always, our webinars are recorded and made available on our YouTube channel. If you'd like to stay updated with all the latest from wolfSSL, follow us on X, connect with us on LinkedIn, and subscribe to our YouTube channel. Feel free to contact us via email at facts@wolfSSL.com if you have any further questions. Before we dive into the technical presentation, I'd like to provide a brief overview of wolfSSL. Today, wolfSSL secures over 5 billion connections. We have more than 2,700 OEM customers and dozens of resellers. wolfSSL consists of over 50 dedicated employees, primarily engineers. This progress is of course supported by a strong partner network that we are very proud of. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO178 support, a FIPS 140-3 certification and a FIPS Ready offering, NQTT up to the V5 specification, SSH v2, TPM 2.0, a secure bootloader known as wolfBoot, Java wrappers, and commercial product offering, wolfHSM. These offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. Now, I'd like to turn it over to Daniela to discuss the basics of wolfBoot and all the advanced things we are adding in the last year.
Thank you, Emma. So, before getting to the actual details, I will just remind what our main areas of focus are at wolfSSL. We secure data, and we secure data at rest with cryptography. We secure data in transit using standard protocols like SSL and TLS or SSH. And we also secure the boot process and the firmware updates thanks to wolfBoot, which is the main brick for our secure boot and firmware update solution. And thanks also to the integration with other products that we will see during this presentation. This is an overview of our core products. Today we are focusing mostly on wolfBoot, but we will also mention wolfCrypt, which is our crypto engine, which also powers wolfSSL, which is of course our flagship product, our lightweight SSL TLS implementation that relies on the cryptography that's offered by wolfCrypt. And we will also mention wolfHSM, one of our newest products, and the integration that we have done with wolfBoot. And this is a special implementation of wolfSSL that offers a client-server model for communicating with specialized core that offer hardware security modules, features and characteristics, as we will see in the details of this presentation. So, what is wolfBoot? wolfBoot is an open source universal secure bootloader for all systems, embedded or not. And secure boot, what it means by literature is just a process that prevents running unauthorized software or firmware on board of your embedded device. So a cryptographic signature is attached to all authorized device that's allowed to be run on the device. And the secure bootloader will just enforce this requirement of having to authenticate the signature of any code that's running on the target system. wolfBoot was born in 2018. The beginning, we started with the first port on Cortex-M microcontrollers. And we based our design on the requirements that later on became RFC 1919. Back then was a draft from IETF, which is mostly oriented for IoT devices. We have done several presentations and webinars as well. You will find some material also on our YouTube channel. And we added support for a lot of different cryptography algorithms, among those that were available in wolfCrypt, and you can see a short list here. Of course, one of the first goals that we have set for us was that the bootloader should have been extremely portable. And when it was very easy for us to integrate the first architecture like RISC-V or PowerPC, etc. But especially it's particularly easy to integrate new ports for specific targets within the architecture that we already support. For this reason, we have about almost 40 targets with full examples and documentation and test applications to verify that the bootloader is working properly. And on top of that, wolfBoot can also run as a library anywhere. So even on those targets that are not directly supported by us. One of the extra goals that we set for our development team at the time was to focus on security. Because of course, as also stated in RFC 1919, secure bootloader is a key component for the security of the entire system. So it is a good idea to reduce as much as possible the surface of attack. And for this reason, we don't allow any dynamic allocations that are usually considered, let's say, a very important source of defects that can be exploited by a potential attacker. And the same way, we don't handle any IRQ unless specifically required by the specific use case where the wolfBoot is operating at. And which also means that we don't usually have any communication with the user like any classic bootloaders, non-secure bootloaders that you may think of, like on personal computers, or also an embedded device like U-Boot, where you have some kind of a console for interacting with some runtime characteristic. For wolfBoot, this is excluded by design for the sake of safety in this case. So this means that all the execution flows are predictable at compile time for that specific use case. And we also have specific protection and mitigations against attacks like glitch attacks, fault injections attacks. And it's about the fault injection attack. What our workaround have been tested using this device, as you see here. It's a chip shouter, which basically can introduce faults at a specific time during the boot process, especially, for instance, to try and skip the verification of the image, which is the key feature of a secure bootloader. And those mitigations that we have introduced actually are able to prevent this type of attack. There are other unique features like delta updates, also supporting the same emergency fallback as the normal updates. We do have encrypted end-to-end support from designer to the bootloader using symmetric cryptography algorithm. And then we have integration with TPM 2.0 devices, thanks to the integration with wolfTPM. It's both to offload crypto, but also to use more advanced features like storing secrets, but also increasing and verifying PCRs for measured boot. And we have certified security, thanks to the FIPS 140-3 certificate that we'll talk about, and the 0178 for airborne devices, for certified safety in this case. And it's very flexible. The key tools that we distribute together with the bootloader are compatible with Linux, Mac, and Windows. We can use, we can offload some signature to the HSM, and we recently introduced the possibility to extend the metadata that are transmitted together with the firmware by adding customized header fields. For instance, if you want to track other characteristic of your the firmware that is going to be authenticated on board. As we said, we follow the RFC 1919, so that means that we are mandated to use small parsers, the manifest header, which is the way we transmit all the metadata, including the signature and the hash to verify the authenticity and the integrity of the firmware that's being transmitted. We have public key-based authentication, of course. The entire security mechanism relies on the trust anchor, and of course we do hash-based integrity verification, so with SHA-2 or SHA-3, but also the RFC 1919, it's very important, mandates that it's not the bootloader responsible for transferring the image physically, so it doesn't have to include all the complexity of the entire protocols that are used for communication, even for as simple as it could be, like the case, for instance, of DFU or a serial port. It's usually a different stage that that takes over this task of transferring the update image before having wolfBoot to validate it and decide if it is worth installing it because it's authentic and it has the right version number. How does the mechanism work? There's a key pair that's usually is generated once. It's an asymmetric key pair, so the private key stays on the server. It's never redistributed to the actual devices, while the public key is stored on the target, and it's what we call the trust anchor, and it's accessible by the bootloader for reading. So the security only depends on the secretness of the unique private key or keys that are used to sign the updates. So as soon as those are kept in a safe place, they are stored in the cloud or in backend or in a specific HSM, like HSM as a service, then there is no risk for the secure boot of the entire fleet. And then the sign tool attaches this manifest header, which, as I said, contains all the metadata that's necessary for the bootloader to assess the firmware for authenticity, integrity, versioning, and all the things that are required by the use case for wolfBoot to stage the image or to decide to overwrite the current image, swap it with the newly received updated version. And as we said, wolfBoot only relies on a trust anchor to embed the public keys used to verify the signature. So this is what happens. Basically, you have a trusted firmware and you want to transfer it on the embedded system. You want the embedded system to be sure that this is signed by you. So we use the private key to sign the firmware as mandated by RFC 1919, and then the public key is used for verifying the signature, and the public key is stored inside the embedded system. There are two types of macro architecture, let's say, supported on a microcontroller side due to the physical memory restrictions. The firmware needs to boot always from the same address. So we need to physically swap, in most of the cases, the two firmware, the old one and the new one. After the new one is received in the update partition, we swap that with the boot partition content, so we keep a backup copy of the previous version. And then at that point, we decide to stage the new version that's now being copied to the boot partition. In some cases, we can use, for instance, an external flash, for instance, an SPI flash, and then the mechanism is pretty much the same, but this leaves, of course, more space for the boot partition that can fill all the space that's not taken by the bootloader itself in the internal flash. That's the one that needs to be executed in place. But the swap mechanism is still the same because there is no need to run any code from the update partition. So it can be in a non-executable, non-volatile memory. And in some cases and some specific devices, there is a possibility of swapping two physical blocks inside the internal flash to be mapped basically to invert the mapping. So the first half gets mapped as a second half and vice versa. And this is a very quick way that's provided, especially for this, but by some of the newest microcontrollers, especially in the Cortex M7 or even M33, where by swapping a single bit, the swap operation becomes very quick, so the updates are basically almost immediate. On CPU-based systems, the situation is slightly different because we need to have two partitions that have basically the same level in the design, calling them A and B, for instance, and they have since they are equivalent, we just run an election process at boot, where the bootloader picks the one with the highest version among those that can be successfully authenticated. So first you check for the version, and then if the image with the higher version can be authenticated, then you stage that. Otherwise, you try with the second one. And of course, this is possible because of dynamic memory mapping, and because usually CPU-based systems execute their kernel or the first stage from RAM. So we can load the kernel to RAM and then verify it in place before staging. And in this case, often we need to interact with the other boot stages, like first stage or even third stages, where, for instance, we integrate in a chain, in a boot chain that already contains an advanced bootloader, but it might be needed to verify that for authenticity as well, like in the case of U-boot, for instance, as a third stage bootloader. So we mentioned this a few times, the word trust anchor. That's basically a subset of the concept of a root to trust. In this case, it's not in secret because it's in fact a public key. And so for this reason, its only requirement when it's being stored is that it needs to be protected from writing. So there is no risk, again, for the boot process, for the secure boot process, if the public key is read out by an attacker, but overwriting it would compromise the mechanism, of course. And this is the whole concept of trust anchor and trust anchor store is well explained in RFC 6024. So since these are the requirements for the trust anchor store, so it must resist modification against unauthorized insertion, deletion, and modification. This is usually a perfect fit with some of the physical peripherals that we find on both CPU-based and microcontroller-based embedded devices. For instance, you can have a trust anchor store implemented as a root trust in a secure element or in a TPM. It could be provided through a separate device or even an HSM, as we will see, and it could even be installed by the manufacturer in the factory stage. One specific use case which is very comfortable and very fit for this is the OTP memory, which is designed for this basically. So it's some memory that some microcontrollers have that you can write only once to, and then it's protected for writing against that forever. So basically it's write once and never erase. So that's perfect to store this kind of object. I mentioned the support for TPM 2.0. That happens, of course, thanks to the integration with another one of our products. It's called wolfTPM, which is our TPM driver, which allows, as I said, to set the root to trust for the trust anchor or for other root to trust that need to be locked, for instance, to sealing a secret. It does have support for measure boot thanks to the extensions and the verification of the PCRs. We can offload some of the cryptographic operations, although this is not always faster than executing them in software. And other features like platform authentication lockout or parameter encryption support to protect the channel. Other interesting feature we have added a bit less recently, we have a port for Tiger Lake 11th generation Intel Core i7, and that works as a replacement for a Slim bootloader that's provided by Intel. So basically, it's a very lightweight replacement for your entire BIOS that runs in the ROM of your x86 Intel Tiger Lake in this case. And this allows for a true non-UEFI, let's say, proper secure boot process that starts when the machine turns on. And this is very important for us. This has also been certified for using avionics systems because of its safety and security, of course. Another important feature that we also offer on a different type of architecture, in this case it's ARMv8 Cortex-M, where we can act as a supervisor for everything that's secure in the system. So as a single actor in the secure domain and expose an API of PKCS11 calls for the non-secure application or real-time operating systems that are running in the application non-secure space to access at runtime. And this, of course, allows for a perfect separation of the two worlds just by installing wolfBoot. That becomes just more of a secure bootloader in this case, but remains at disposal of the application for any secure operations. And of course, the big advantage of this is that the non-secure application can also be less trusted because they will never handle any secret content, any private key or secret symmetric key directly, but they will ask for specific operations using those keys that are stored in a secure domain and can only be accessed referring to them by their slot number. So we finally are to the what's new section. So what is the improvements and new features that we have recently introduced? As I mentioned before, the biggest headline, of course, was the FIPS 140-3 certificate that was awarded to wolfCrypt last year, the 11th of July, actually. So a little shorter than last year, than a year ago. And this is, of course, very important because it allows us to use the FIPS certified cryptography in all the products, and of course, wolfBoot is no exception to this. The 0178C certification for wolfBoot in combination with wolfCrypt that had been already certified to the 0178C in other specific avionic projects. And we added full support for ELF file scattering, so you can authenticate an ELF as a single, let's say, contiguous firmware file and then scatter it to different locations according to the sections in its header. And then the next time the machine powers on, it can verify the ELF by recollecting, regathering all the components and to recompose basically the original image as if it was contiguous. And this is very important for those systems that load ELF files in memory into different locations than that are not contiguous. We have improved the management of the Keystore, also to accommodate different type of integration with different types of HSM and secure elements. We have the support for TP flash memories. We already went over this, how important OTP is. We added the custom tags to the manifest header. And we made big steps towards post-quantum secure boot and specifically hybrid post-quantum plus conventional secure boot, which is the recommended way of switching to those new algorithms, as we will see in a few minutes. And we also added support for wolfHSM that I mentioned at the beginning is one of our newest products, and it's very important for a few specific use cases with a specific hardware layout. wolfBoot can now be provided, as I said, as FIPS 140-3 certified module. You can find our certificate for 4718 on the NIST website, and also all the operating environment that's supported, the CIVP, and all the information that you might need on this certification process. For the A178C certification, as far as we know, wolfCrypt together with wolfBoot is the only D0178C certified secure bootloader solution which is available nowadays. And there is a few reasons, of course, why you should migrate to wolfBoot from your existing bootloader, especially if you are running in a safety critical scenario. And some of those we've been already over this, so I won't spend any words on this. So of course the Keystore contains the trust anchor, because the Keystore is the element, the abstraction that inside wolfBoot that contains those public keys. And then, but that doesn't have, let's say, it has a default placement which is within the wolfBoot code, when in those simple cases where you can just protect the entire wolfBoot partition because you have no way to verify that from a first stage bootloader, for instance. You can protect that from writing, so otherwise an attacker could just overwrite your secure bootloader. And at that point, if you're using this mechanism, it's probably convenient to just have all your public keys that you want to use at runtime just as part of the code of wolfBoot itself. But there are, of course, many other options. So we mentioned OTP, but of course you can have a write protected flash somewhere else. You can have a TPM with a locked root of trust, an HSM, or even a neighboring system that's suggesting the public key or providing the public key with an API through a serial port or something like this. Since it's not secret, it can be transferred safely using, let's say, local communication towards other devices that live around the target. And of course, there is HSM, and we can integrate secure boot with wolfHSM. The typical use case for wolfHSM is when you have, for instance, an heterogeneous multi-processor target, which has also usually a dedicated core that manages crypto and the secrets for you. And this dedicated core also often is the only core that's allowed to talk to any secure elements that are connected to the system. So basically, it's used to centralize all the crypto operation in one single point and also to distribute all the services, all the crypto operations as services for all the application cores that might be on the system, and also set priorities in a client-server fashion, basically. So the server is going to run on your crypto dedicated core, and the clients can run anywhere at all stages for different use cases. Some of the possible scenarios that we have explored and demoed so far include wolfBoot with the server-only wolfHSM, wolfBoot connected as a client to wolfHSM, both of those together, and a fully integrated solution that we will quickly go over. So this is the generic wolfHSM architecture. As you can see on the left-hand side, there's all the HSM secure area. So you have your HSM core that can communicate with these black boxes on top that are crypto accelerator or other secure elements that might be physically accessible only by the HSM core. And then we have a RAM that's not accessible by any application cores, let's say, and it's only used by the HSM, and also some non-volatile memory that we can use for storing the crypto vault. On the other hand, on the other side, towards the right, there are communication buffers, can be any kind of communication protocol to connect the cores. Usually it's an internal bus, and usually also have a shared non-volatile memory where you can save the state for specific operations. And then at that point, through the APIs, the client-server APIs between the two sides, each core can have one or more applications that can access the HSM core using this infrastructure. So when wolfBoot is used with wolfHSM as a server, the platform security is responsible to loading wolfBoot, and the wolfBoot loads wolfHSM server and authenticates it. And at that point, it's wolfHSM that starts a single CPU cores one by one when it's ready. So, and the client applications will be capable of accessing the wolfHSM server. But as you can see in this case, the keys for wolfBoot are outside of the wolfHSM because they might be stored in a OTP or in a specific key store, but they are not managed by the wolfHSM server. While in the other case where we use wolfBoot as a client, as well as the applications are used as a client, so it's the platform security that loads the wolfHSM on the HSM core independently. Another point, wolfBoot can use the wolfHSM client to the wolfHSM bus to retrieve those keys that are needed to verify the client application. And when a client application starts, of course, you can still use a wolfHSM client to access the same cryptography as a wolfBoot. Of course, you can have the two things at the same time, where wolfBoot is started on the on the HSM core, and it's used to authenticate wolfHSM that has some keys, and those keys can be used as a client by wolfBoot to authenticate the client application on the client core, on the application core. Even a bit more complicated, there's the completely integrated wolfBoot HSM solution where it's wolfBoot that gets loaded but also contains the wolfHSM server itself. So it has its own keys, but also the keys that can be distributed to other wolfHSM clients. And then there is a second stage wolfBoot that uses that key, those keys, the purple keys in this case, to authenticate the client application that can finally use its own green keys from the application for performing the crypto operations that the application needs. We mentioned that one of the most important features that we have added recently and evolved have been the support for post-quantum secure boot. So it's post-quantum algorithms. This is some task that's been going on for a couple of years, as you can see, on both sides, from wolfCrypt and wolfBoot side. So at the beginning, back a couple of years ago, wolfCrypt had a wrapper for the reference implementation of those new algorithms like LMS, HSS, XMSS, and others. And at that point, we added the support for hash-based signature scheme support. So these two hash-based algorithms that we will see shortly. And then later on, we more recently, a year ago, completed the migration from the reference implementation, the freeware reference implementation that was available for testing during the NIST phase of evaluating those post-quantum algorithms to our own implementation, our very own implementation in wolfCrypt for most of our algorithms, including LMS, XMSS, but also MLDSA and others. And this, of course, means that those algorithms are much faster. They are not just for demonstrative purpose like libOQC, but are actually for using production, and especially for using production in those embedded devices where let's say the performance are very important, and we know that. So the same kind of optimizations work that we have done for classic algorithms has also been ported in large part for these new post-quantum algorithms. And a bit more recently, we also integrated MLDSA and hybrid solutions where we combine classic and post-quantum signature in the same device. Just a bit of classifications of those new post-quantum algorithms that we have introduced. During the post-quantum standardization, NIST had some kind of side path by including together, coordinating with the IETF, a couple of algorithms that did not cover one of the specification for the selection of these new post-quantum algorithms, but still were worth considering. So those algorithms that were included are hash-based. So even if they are older than the lattice-based, for instance, newer post-quantum algorithms, they are still quantum resistant. They are very well studied, so they are old, and they have better performance because they are based on SHA operations that are usually much more efficient on the verification side. Okay, the key generation might be very slow, but this is done once, as we've seen, so that's not a big issue in production. But the most important warning, if you're using any of those algorithms, is that it's absolutely mandatory to use some state management, because since these algorithms are stateful, it means that every time that you use a private key, the private key changes a bit. And it's not possible to use the same private key twice to sign two different firmwares, for instance, because that's a vulnerability by definition. So it can lead to catastrophic, let's say, results if you don't take care properly of this. But this was important as a step because it paved the way for digital signature scheme PQC migration. So this were the first algorithms that we have added, XMSS and LMS. They've been standardized by IETF recently. As you can see, there are Cs for both. And then, of course, also recommended by the NIST in a specific format, HSS and XMSS MT. And some of the parameters have been approved by NIST for these algorithms that we support. The official PQC algorithms have been supported by NIST are actually these three, and the FIPS 203 is MLCAM, that's derived by Kyber, MLDSA, FIPS 204, that's derived by Dilithium, and 205, that's derived by from Sphinx. And of course, this is the perfect fit for wolfBoot because it really looks like the classic algorithm. So it's a public key classic algorithm, basically, but it has post-quantum resistance power. So this is the algorithm that we decided to add next, and of course we have integrated that in wolfBoot as well. So you probably know this already, but the NSA in the CNSA 2.0 document published back in the day, it recommended that we absolutely start migrating to post-quantum cryptography secure boot by 2025, which is already ongoing. And it suggested, of course, at first the XMSS and MS stateful algorithms as well. So you can see this was the proposed CNSA timeline and software firmware signing. That's what we are looking at today. The line is already solid at the start of 2025. So what normally, what I was talking about, the stateful signature there. So what normally happens on a secure boot without those stateful algorithms, is that you can basically have the key generation on your own and then reuse the same private key all the time to sign all the firmwares. And this works both with conventional algorithms and with stateless post-quantum cryptography like the MLDSA just introduced. But it doesn't work with the stateful PQC, so RMS and XMSS. What's the requirement in this case is that you have an HSM as a service in this case, so not an actual locally running HSM, but in the cloud. So someone that's keeping your private key and also keeping the state for the LMS or XMSS key, so that you just have a mechanism through the sign tool wolfBoot to offload those signature to a third party. It could be a HSM, for instance, in this case. And this allows this mechanism, this extra step, let's say, in this mechanism allows you to use those stateful post-quantum cryptography algorithms in wolfBoot safely and securely. Regarding the migration towards post-quantum, it's of course that we can't just interrupt stop using all the classic cryptography and start to use something completely new tomorrow. But we need to act as quick as possible because not just in the context of secure boot, but there are some immediate concerns because people could already start collecting encrypted data today, and with the opportunity of decrypting those keys that generated the ephemeral keys later on, and being able in some way to decrypt the content that's been harvested now. And also, of course, the deploy and forget, which is actually affecting secure boot in these cases. So think about a device that's shipped today, but it has 20 years expected on the market. That for sure we will have post-quantum computers by then, and probably the algorithms that we set today are not sufficient to guarantee your secure boot later on when those computers are out. So what are the best migration paths for this, and what the list also recommends is to use hybrid signature schemes. So combine the classic elliptic curve signature authentication with a post-quantum cryptography using a dual algorithm signature verification. So two steps, one with the classic one and one the post-quantum. Or, for instance, use hybrid key establishments, so the same mechanism, but for derivation of the symmetric keys that you use for encryption, or other countermeasures, double the symmetric key size. But of course, we need to be always within the FIPS 140-3 compliance. So the solution that we adopted is the hybrid signature scheme in wolfBoot. So we allowed to have, instead of one single key pair, we have two key pairs. So there is one that's a conventional, classic, for instance, a CDSA or RSA, and one that's a private key that's from a post-quantum cryptography. For instance, the best in class CNSA compliant would be MLDSA 87, which is the biggest key among those that are standardized for this dilithium derived algorithm, with ECC 521. So this is probably the strongest hybrid that we can offer today, and that's and there are examples in our repository on how to do this. So to conclude this, wolfBoot is not just only the universal secure bootloader, because it can be distributed as a FIPS 140-3 module. It can fly. I don't know other secure bootloaders that can do that because of its DO178C certification. On some ARM microcontrollers, we can act as a trust zone M manager and supervisor for the secure domain and offer access to security in a secure way through wolfPKCS11 secure engine. It's either using OTP or other trust anchor stored in another Keystore of your choice. We have the integration with wolfHSM, and we are exploring all the possible combinations, as you can see. We have a post-quantum ready secure boot solution, but not only that, we have the best post-quantum migration strategy for a secure bootloader, thanks to the hybrid post-quantum plus conventional secure boot mechanism. So this concludes my presentation, and as we said, there is a Q&A interface, so I'll be happy to answer
How to
questions.
create keys and sign the image? Is there a tool/script available? And how can I try this open source hardware like STM32F series device?
Wonderful. So yes, there are the tools for signing and generating the keys are included in the wolfBoot distribution. If you look in the tools/key tools, there is there are the C source codes for both of those, but we also distribute binaries, for instance, for Windows, because if you don't want to go through the Visual Studio solution and compile it to yourself, we do have exe files for that. And yeah, basically those tools are compatible with Linux, macOS, and Windows, and you can use on all of those. There is the manual inside the documentation. You can see that there is a signing manual with all the options that you can use there. And for your second question, where you can get that, of course, you can download the wolfBoot from our website, but you can also clone it from our GitHub repository. And there you also will find in the documentation a file called targets.md. And if you look for your specific STM32 Series F device, you will find that or a very close one, and all the instructions step by step on how to test wolfBoot, how to create your own keys, and how to sign your firmware, and how to do all this in one single make command to test it straight away, right away on your target device.
Wonderful. Is this one's kind of similar, I think, but I'm not super technical. So, is there a sample code to try signing this boot in MCU or QEMU emulator?
Uh, Yes, I think we have Kimu examples. One is with Raspberry Pi related image. The other one is with EFI demo, so for x86 Kemu. But we also use extensively another emulator, which is Reno.io, which is an open source project as well, supported by the Linux Foundation. Maintained by Ant Micro, which is one of our partners. And we use that a lot for continuous integration. This is basically the KEMU of microcontrollers. So you can choose any STM32 Nordic NXP device that they support, and basically start that with all its peripherals. And wolfBoot is tested through this as well. So if you don't have any hardware at hand, you can try that on Camu, you can try that on Renode, but we also have some synthetic targets like the simulator. So you will see that there are in the config examples directory a lot of files that start with the sim underscore something. That's a simulator, which means that wolfBoot will run as a process on your Linux machine, and then you can start it as if it was basically a program, and then it will authenticate the image of a flash that contains another elf, which is another program, so you can see the entire chain without the actual burden of having to deal with the hardware at that point. So you can actually run that through a debugger and see step by step what the bootloader is doing, how it's authenticating and verifying the integrity, etc.
Wonderful. Is the wolfBoot compatible with the specification of the Resilience Act?
Oh, yes. In fact, I would say that the specifications are overlapping with what was written back then on RFC 1919. So what the CRA wants you to do with your devices to be able to commercialize those in the European Union is that you have to provide a strong secure boot mechanism, which is based on a trust anchor, on a public key mechanism. So it's uh, ditto exactly word by word what we have seen so far. It's contained in the CRA specification. So in short, yes, that's a shortcut to comply with the CRA on an existing product, for instance.
What was the name of the QEMU for micros that was mentioned?
Oh, it's renode.io. It's like renode.io.
Perfect. Is it possible to sign different partition of the same systems using different keys?
Yes, so the Keystore not only allows to have multiple public keys, but there is a field that you can set, which is a permission mask, and that's a bit mask. So every bit corresponds to a specific partition and a specific with a specific ID. So the sign tool can add an ID to a partition to an image to say that belongs to that partition. So for instance, 0 is reserved for wolfBoot itself, which can actually update itself if needed. 1 is usually the first image that gets staged, and then the numbers from 2 to 15 are free to use for any other partitions. And at that point, you can have different classes of keys that can selectively authenticate only a subset of this partition, or only one of those partition, or all of them, for instance.
Perfect. Can I use a microchip TA100 as a root of trust?
Yes, yeah, we do have integration that with wolfCrypt. So actually, all secure elements that provide some way of root to trust or trust anchor can be easily integrated. If they are already supported, like the TA100 by our wolfCrypt library, this is kind of trivial. But of course, if you also have some secure elements that are not directly supported, please contact us. This is usually a very viable and usually not very, let's say, time-consuming port for us to provide. And it's in our interest, of course, to have as many of those devices, secure elements supported directly in wolfCrypt. So not just wolfBoot, but the entire wolfSSL ecosystem of products is able to use those components as well. So yeah, we do have customers that use the TA100 as a root of trust, as a trust anchor. Actually, TA, it's in the name itself. Successfully to authenticate their boot procedure.
Wonderful. Well, thank you so much, Daniela, for hosting an informative webinar. Thank you to everyone for joining. I will email a copy of the webinar recording and PDF slides. You can keep up with our upcoming events, meet our team in person, read our blog posts, and get the latest wolfSSL updates by following us on X, connecting with us on LinkedIn, and subscribing to our YouTube channel. If you have any questions, please reach out to us at facts@wolfSSL.com. Thank you again, and we look forward to seeing you on July 16th for our webinar on TLS over Bluetooth with wolfSSL, why you do it and how easy it is. Thank you all.